Yeah, a warm welcome to everyone. I'm sure participants join from all around the world. So, good morning, good evening, good afternoon, depending on where you are. And yeah, a warm welcome to this 2022 and the first event for our ComSoc Bangalore chapter. And we are lucky to have Professor Melke's talk first and especially on the very relevant topic for today, deep and reinforced learning in 5G and 6G. Myself, I am Ganeshan Tyagarajan. I'm chair-elect 2021. I'm here to take over for this year, right? And this particular chapter is very vibrant with a lot of practicing engineers, academicians, students, and thanks to all the hard work for the previous Exicom that we have been able to get uh, the section chapter performance award for this Asia Pac region for 3 consecutive years. And this year, 2021, we have the Year of the Chapter Award. So that kind of talks about the type of activities and learnings that's going on in this chapter. And I'm sure this year also going to be a lot of such learning. And with all your participation and the eminent speakers from all around the world and in India as well, and it makes it possible. So without much ado, I'd like to introduce the speaker for today, Dr. Melke. Um, she is a Tier 2 Canada Research Chair in AA-enabled Next Generation Wireless Network. And she is also assistant professor, associate professor at the School of Electrical Engineering and Computer Science at the University of Ottawa. She is the founding director of the Network Systems and Communication Research Laboratory. She has over 140 peer-reviewed publications, which have been cited over 5,000 times, and she has an H index of 37. Recently, she was elected for the 2019 list of Young Women Stars in Computer Networking and Communications. She has received several awards, Best Paper awards, including the IEEE Communication Society Best Tutorial Paper Award in 2017. And she is the co-editor of 3 books on smart grid, smart cities, and intelligent transportation. She has delivered numerous plenary talks, keynotes, tutorials, and seminars around the globe. She serves on the editorial board of several IEEE transaction journals. She has acted as a general chair and a technical program chair for many international conferences and workshops. Her main research interests are AI-enabled wireless networks, 5G and 6G wireless communication, smart grid, electric vehicles, Internet of Things, and wireless sensor network. She is a senior member of IEEE. And I'd like to welcome a professor on behalf of ComSoc Chapter Bangalore, ComSoc Chapter Hyderabad, as well as ComSoc Chapter Kerala. So over to you, Professor.
Thank you very much for this nice introduction, and thank you very much for inviting me to give this distinguished lecture. Let me start by sharing my slides. I believe you are now able to see the slides, hear me, and also see me on the camera.
Yes, loud and clear. Yeah.
Thank you. Perfect. Now let me get the screen. That little screen that has me on the camera in a proper position. All right. So good morning to those of you who are in India and Far East, and good evening for those of us who are in the Eastern time zone. It's a great pleasure to be here to deliver this IEEE ComSoc Distinguished Lecture for the IEEE ComSoc chapters Bangalore, Kerala, sorry, and Hyderabad. Today I will be talking about deep and reinforcement learning in 5G and 6G, where we will be touching on very hot trends actually in wireless communications. And I will take you to a journey from the 5G, which is the current deployments of wireless networks or mobile networks around the world, to the planned deployments for, or planned developments, let's say, of the 6th generation. So first of all, let me get started by saying that staying connected or being connected became one of the most important paradigms for all of us to contribute to the economy as the pandemic took us on hold for the past 2 years. So many of us have been working from home and we have been relying on communications. And I remember last year, at the times when pandemic were at the peak rates, several people were, flying away from the busy city centers to the urban areas. And soon they were faced by the connectivity challenges. So they were not having good quality of connection. So Zoom meetings and the others were being quite glitchy for them. So that means we still have those challenges in wireless. We can't say we have solved all the challenges and we have a perfect pervasive coverage. And we already see that, as I said, in rural or remote communities. Even in Canada, we have this problem that we call as digital divide, where not every place has the connectivity in the same level. And that impacts, for instance, digital agriculture, that, IoT technologies that can be used and can improve, for instance, farming, are not used to the full potential. Or communities who are remote, and especially, northern Canada, if you think about it, and I'm sure there is the same situation in India and many other places around the world, for remote communities providing the same. Yes, WebEx gave me a message. I don't know if you had the same thing, but yeah, let's continue. So yeah, with the need for connectivity everywhere in dense city centers or rural remote areas, so we all face the importance of communications. And there is another end of the spectrum I would like to call, where, from rural communities where communication might not have been such a big deal for a very long time, but now that it is really important. We have been all this high tech around production manufacturing, but we did not have the smart production capabilities that we have as of today, or we would like to have tomorrow with the 6G. And this is all about creating a digital twin of a factory, working on it on a digital environment, monitoring and controlling a full factory floor with the help of wireless connectivity. So as you can see, these examples, we can talk about these motivating examples, I guess, for an hour or two, but we all see the need for being connected. Then, of course, the current deployments, we are still working on 5G. 5G advanced standard is being worked on these days. And within the next 10 years, well, it's already 9 years now, I'm sorry, 8 years now. For 2030, we're planning the rollout for 6G. And if you listen to other talks, people talk about a lot of potential technologies that will be in 6G. Of course, we don't have, or I don't have at least, a crystal ball to look at and tell you, which one will be the prevailing technology, but at least I can provide my perspective. I see that using semantics will be of great importance because more and more we are seeing that networks, as they operate and try to optimize themselves, there's so much that we can do without the knowledge of the applications or knowledge of where the user is. So the information that is coming around from the contextual places, which we call as the semantics, will be very, very important. And it will be in interaction with the techniques that we design for AI and machine learning, which is at the heart of this talk. So many of us expect 6G to be AI native and have much stronger automation than the previous generations. Now, what do we mean by this? Let's talk about this being AI native or network automation a bit. When we talk about AI, which stands for artificial intelligence, these are the types of techniques that computer scientists have been working on since several decades. And there has been various types of artificial intelligence techniques like supervised learning, unsupervised learning, reinforcement, and deep reinforcement learning. And all of them has their own importance, feature, and help in different kind of problems. But at a time when people were doing AI research, one of the first common systems were expert systems. And the belief at that time was that if we give all the rules around the world of us to a machine, the machine will become as intelligent as a human. But soon after, researchers noticed that this is not how human learning happens, because not everything is written in books, right? We are born, we try things, we interact with the world, and we learn from the world. So if we think about giving all the rules to a machine and making it intelligent, that quickly proves itself to be actually inefficient or not making good use of that interactive learning that we have in humans as well as animals, by the way. So sometimes you would hear people talking about making machines as smart as cats or dogs. This is the reason. I mean, we share some common intelligence or the learning ways with the animals, and reinforcement learning in particularly is one such technique. And the word reinforcement is actually also appears in the trial and error experiments of Pavlov, where many of you would know he would treat a dog for a good behavior. He would give a treat for a dog for a good behavior or punish to reinforce a certain behavior. Just like that, we can actually give a reward to a machine to reinforce it to work in a certain direction. So what do we mean by that? And after this part of the talk, I will be focusing on reinforcement learning and deep reinforcement learning. So if we try to bring it to the perspective of a machine, for example, we have an agent. Agent interacts with the environment. The environment, this interaction is called an action. After this interaction, the agent receives a reward and the state of the agent changes to the next state or moves to the next state. And if we think about it as a trial and error thing, that's a one-time event. But in reinforcement learning, we usually talk about number of repeated attempts so that we can try out all these possibilities that you see on the right hand of the slide, where there are certain branches that are in regular arrows and certain branches that are in bolded arrows. These bolded arrows tend to show the optimal policy or the best path. Let's call it the best path for now. So that selection of, first go to a certain node or certain decision and then take another decision, this is kind of a sequential act where we call as the policy. So the whole sequence is called as the policy. And now let's think of chess, the game of chess, because the full development of reinforcement learning techniques have a close relationship with the chess playing machines or Go playing machines or backgammon playing machines. So human versus machines, playing games and trying to design the best algorithm to beat the humans have been one of the driving forces of the research behind reinforcement learning. Now let's go a little bit deeper into reinforcement learning and define, a couple of fundamental things. To be able to do that, we have to go back to the Markov decision process theory. I'll try to be not to be so boring, hopefully. I will use less formulations, but let's stick with the basics of the technique for a little while, and then I'm going to show how we use these in wireless. So ST is the state of the action, state of the agent at time t. AT is the action taken by the agent at time t. And then how is the reward received? A reward RT plus 1 is received when the agent takes action AT in a state ST. The next state becomes ST plus 1, and the agent in that case receives RT plus 1. If we have a deterministic system, every time the agent is in state ST and takes the action AT, it should switch to the next state ST plus 1. However, in certain systems, this won't be the case. So we will have a next state probability where we denote by over here with this equation. And let me get a pointer here. We will see that given that an agent is in state ST, takes an action AT, it will move to the state ST plus 1 with a certain probability. This could also hold for the reward. The agent doesn't have to receive the same reward as it takes the same action in the same state and moves to the same state. It may get a different reward, so the reward could be probabilistic as well. If we know the environment, so if we can model the environment, we can know these actual values of the probabilities. But if it is an environment that we don't have the model, this time we are not in trouble. I don't want to say we're in trouble, but we have to resort to some other techniques. But the development of machine learning techniques started with the deterministic models, then probabilistic, where we have the model, we know the probabilities, and then moved on to systems, which we call as model-free techniques, where these probabilities are unknown. And a couple of more definitions. An episode is a trial of actions from initial state to the goal state, and the policy defines the agent behavior, basically which actions are taken in which sequence. That policy is very important because at the end of the day, we need an agent that maximizes the value of that policy, becomes a winner policy in another word. So we define policy as a mapping from states to actions. Every state has every policy has a value. And this is a numeric value, so it's like a number 5, 10, 12. Then how do we calculate that numeric value? It is through the rewards. The cumulative expectation of the rewards gives the value of the policy. For a finite horizon game or finite horizon learning problem, we actually don't need to use those gammas. These gammas are discount factors. They are between 0 and 1. We don't need them if we have a finite horizon situation. But for an infinite horizon case where we have to accumulate all the rewards, then what we would like to do is, let's say our game will take 100 steps. We want to be more careful about our next step or the next steps rather than our maybe 80th step after this one. So the future steps, future actions that will be taken and the rewards that will be received from those future actions should have less significance on my overall reward. That's why this discount factor grows for larger index rewards. Now, if we do some algebraic operations, we can obtain the Bellman equation, which Richard Bellman came out around 1950s for optimal control theory problems. And over there, he formulated the problem like this. V star, which is the optimal policy, is found by the action that maximizes this equation. This equation is actually the summation of the rewards, nothing else. But we have a probability for the next state transition. We have the good old gamma over here, and V star from ST plus 1. So if you look into this carefully, if you organize like take gamma out, RT plus I out, and then leave the rest of the formulation inside, you can get V star in a recursive way. This can be perfectly solved by dynamic programming. If we know P, if we know the model, if we know the next state transition probability, we can solve it by dynamic programming. But most of the times in wireless, we are not that lucky. We don't know the model, and actually that's the essence of it. I mean, we have some channel models. We could have used those, and for decades we have been using those. But now that we have more data, we have more interactions with the environment, we can have learning systems, adaptive systems. And that's why we don't want to use models. We want to use a model-free learning technique. And if you are, for example, doing your research for the first time in this area, wireless communications and AI-enabled networks, you would be amazed by the number of papers that use Q-learning. And that is the reason. Q-learning is the simplest model-free reinforcement learning technique. It uses a similar formula to the Bellman equation that I showed before. The only difference is that we don't know the V star, we don't know the probabilities, and for that reason, we use a temporal difference equation to basically mimic the behavior of gradient descent and calculate the Q values, the optimal Q values. The optimal Q values apparently uses the Q values of different states and actions. So that should also, stay in our mind, because I'm going to come back to this problem. That requires the Q learning techniques to store the Q values for all the states and actions. Now, before we see how we solve this problem, I have to explain one more thing, which is the exploration and exploitation in temporal difference. That is something that we use a lot in Q learning. And the reason is that we want to save our agent from a local optimal point. So a very common technique used is called epsilon greedy. Epsilon is a small number. With probability epsilon, we choose a random action, which may seem risky, which may seem not too optimal, but the whole purpose is to drive our agent to a different direction and search for better rewards in that direction. And with probability 1 minus epsilon, we go with the safe and sure way. So we say, okay, this is the optimal action that I see from my Q table, so I'm going to go with the safe route. And we dampen this epsilon value so that we don't have any divergence in learning. So now let's get back to this problem of Q tables. Now, if we have very few states and very few actions, which may not be always likely in wireless communications, we can still use Q learning. There is no harm for it. But as the state action space grows, or if the state action space is continuous, so when it's discrete, it's safe to use Q learning, but for continuous actions in space, we cannot use it. We got a problem there. We have to resort to other techniques. Now, let's see what we can use. Well, first of all, let's think about it. We have a Q table that has some values, and it is a huge table if we have large states and actions. What can we do to save some time? What do we do when we have large data? How do we model? I mean, the simplest way is to apply linear regression, right? You just do linear regression, you get two parameters to represent your whole data. Just like that, we can use a filter, okay? And neural networks are great filters. So we can use a neural network in front of a reinforcement learning algorithm to drive or to approximate the Q table. And that is a technique that we call as actually deep reinforcement learning. So rather than storing the whole Q table, we're going to put a neural network to estimate the values of the Q table. Now, a very brief introduction of neural networks. It's of course a very wide topic, just like reinforcement learning is. But I'm just, summarizing the very fundamental things that's going to be needed for explaining the techniques that we use in 5G and 6G. So the idea of neural networks goes back to 1950s and 60s, where Frank Rosenblatt came up with this idea of a perceptron, which is basically a decision circuit. We have certain inputs. Those inputs come with certain weights, as is not shown in this plot, but the weights are shown in this equation right next to it. And then there is a decision function over here, which is very simple in this example. If the weighted sum of the inputs are less than a threshold, the output is 0. If the weighted sum of the inputs is greater than a threshold, the output is 1. This is one of the very basic activation functions, which we don't use much. So we use either sigmoids or different functions depending on our problem. But just to give you an idea or where they come from, this is one representation. And this perceptron can be considered as like the archaic version of our neurons and the neural networks, where we actually put the neural network units in layers and connect them in different ways. So as you see over here, this is like a feed-forward neural network, a very simple one with just three layers, input, output, and a hidden layer. And whenever we have a hidden layer, we consider this as a deep neural network. And the whole process of learning is actually estimating these weights. So we are trying to estimating or learning these weights. With the neural networks, what we try to do is we have some inputs. We want to classify it to an output. And while doing that, the learned parameters are the weights of these arrows. Now, according to universal approximation theorem, we actually don't need the layers. That might be a surprise. We can put all the neurons in one layer, but too many neurons, and approximate any function that we like. But that would require too many neurons. So putting them into layered architecture actually have helped machine learning scientists to come up with innovative models and to come up with filters that actually model the data in the best possible way. There are many architectures of neural networks. I'm going to talk about a specific one, which is also used in NLP, natural language processing. It is called recurrent neural network. And this type of neural network, the importance of this type of neural network is that it can remember the past. So, and if you think about it, it's actually quite intuitive, right? So a language, there's a pattern in a language, it keeps repeating. And in a network too, some situations keep repeating. So RNN type of neural networks are quite useful in our research as well, just like it has been very useful in NLP research. And one very famous type of RNN is an LSTM. LSTM stands for long short-term memory. And the beauty of LSTM comes from the fact that it has an input unit for memory and a regular input unit as the output of the previous cell. So let's put all of these out there. This input unit, as we call as the memory from the previous unit, goes from a forget gate. Or you could call it alternatively a remember gate, but it doesn't really matter. So basically, this forget gate decides how much of this previous memory should be passed over to the next unit. So step by step, there is a memory that is being carried over to the next units. And this helps the neural network to remember what has happened several steps or maybe 100 steps earlier. Now, this LSTM will become handy because we're going to use them in deep reinforcement learning. Now, let's go back to the place where I said, we have reinforcement learning, we have a Q table, we don't want to store that full Q table. How about we have a neural network? Now I'm saying, how about we have LSTM as the neural network that's driving the reinforcement learning agent. So I think the stones are now fitting into their places. But before we move forward and go with, showing how these are applied, I want to talk about a specific deep reinforcement learning architecture that has been introduced in 2015 by Google DeepMind researchers in Nature. And this is a very, very fundamental paper on deep reinforcement learning. And the reason that it's very fundamental is because the way that I described it before, like we put a neural network in front of the reinforcement learning agent, is not exactly like that. It doesn't work like that because it creates instability. In this paper, they proved like if we have a deep neural network and a target deep neural network, which we copy the training values at certain intervals and keep a copy, basically keep a backup of the weights of the previous neural networks, then we can obtain stability. Another thing that was motivated there was the use of experience replay memory, which gives a mini badge for the reinforcement learning technique. And as you can see here, I have the GNB, but it could have been a chess playing machine. I mean, this architecture is really very generic, but because I'm using it for wireless networks as well, this is a GNB, which is a base station for a 5G network, and the environment in our case is wireless. So after this point, I'm going to switch gears and I'll start talking about wireless. So as I said, we're going to be using these machine learning techniques in 5G and 6G. But now let's talk about why we need to use those techniques. I mean, why don't our regular algorithms perform well in 5G? What is different? This is actually an old picture from ITU, International Telecommunications Union, probably drawn 10, 15 years ago when the 5G use cases were first considered, but we still, consider these three major use cases, which are at the corners of the triangle: enhanced mobile broadband, massive machine type communications, and URLLC, also, which stands for ultra reliable and low latency communications, because they tend to represent what the killer applications of 5G will be. So, I mean, it's always very hard to define what a killer application is when we talk about a next generation. But now that we have 5G already in place, so we are more confident that we can say, for example, augmented reality, XR, AR are just boosting these days, and they are the type of enhanced mobile broadband plus URLLC. They generate traffic, eMBB and URLLC traffic. We are seeing autonomous vehicles, a lot of developments about autonomous vehicles. Although we don't have the fully, autonomous self-driving car, we still, there's an anticipation for 2030 and beyond that. And that requires very low latency. Also in smart cities, connectivity of a lot of devices. So there are lots of things that are challenging for mobile networks, a lot of use cases. And we will see how machine learning techniques will help us to solve these problems. And back to one of our first slides. So I'm going to now talk about AI native or AI-enabled wireless networks. And why network automation is important, and plus wasn't it important before? And this is something I get asked a lot as a Canada researcher in AI-enabled networks. People tend to ask, I mean, this is an exciting area, yes, but is this the first time we are doing automation, or is this the first time we're applying AI/ML techniques? As for automation, we actually have something called self-organized networks in LTE, which is defined in the standards of 3GPP. So that level of automation is not new. But what is new is that the complexity that we get with 5G and the complexity that we will get with 6G will just keep increasing. Is too huge that even the SON algorithms or some adaptive thresholds does not answer our needs anymore. The challenges or the things that come with 5G, for example, with millimeter wave, small and directional cells, because of the propagation limitation of millimeter wave, we have to focus the beams in a certain direction, and then that creates directional cells and also shorter or smaller coverage cells. We have massive number of devices from MMTC type of traffic or use cases. We have massive MIMO, which creates actually a lot of challenges, and we have very good research on the file layer from lots of researchers around the world that try to solve MIMO problems, basically channel estimation problems, by using machine learning. And then another side infrastructure, which is actually becoming a core infrastructure, a very fundamental infrastructure for the next generation networks, is the mobile edge computing or multi-access edge computing. Now that we cannot think of anymore the equipment that is used in the field as just base stations with no processing capacity. Usually a base station comes with a lot of processing capacity on board, and then there are the edge servers, and there is the core cloud as well, or the central cloud as well. So all of these, like how to make the best use of the MEC, is one of the complexities that we see in 5G. And then the virtualization of the RAN radio access networks and ORAN open radio access networks through, for example, the non-real-time and real-time RIC, their design, they're all posing a lot of challenges. Network slicing, although most of the problems we solve for core and transport, we still have the problems in RAN edge and cross-domain slicing. And the place that we want to be in the future is actually AI-enabled networks, where we solve all these problems by using data and that, we can configure our networks. We can have algorithms that can configure the networks on the fly by using interactions with the environment and data from the environment. So in 2019, we published a survey type of paper in IEEE Vehicular Technology magazine, and we outlined these techniques there. And it goes back to actually 2015, where we started doing research in this area. And at that time, we were trying to optimize the communication systems for a smart microgrid, where we actually needed to have much more lower latency than what can be provided by LTE at the time that we were using LTE, of course. Now, I'm going to start talking about a couple of fundamental things which are going to lead us to our papers. And one of the first papers that I'm going to talk about today is a paper from 2019, which was published by or co-authored by one of my PhD students at the time. And that focuses on the fundamental problem of resource block allocation, or PRB allocation, as some of you may know, in 5G. So PRB allocation is this. In OFDM, we split the time and frequency resources in such a way that we can give these resources, a couple of consecutive resources, to the user. So we can group them and assign them to the users. The base station is the one who makes these decisions, and it tries to maximize the whole capacity while taking these decisions. Since we're talking about frequency splitting and time splitting, it's easy to understand that not all subcarriers of OFDM are the same quality. So if a user wants high rate, they should get the better or less SANR, high SANR subcarriers, or if they are, for example, of URLLC type, then they should not wait too much for the EMBB traffic to finish. They should probably puncture some resources, so make a hole in the assignments and grab a resource and finish quickly with their transmission. So that's actually a big problem, how to schedule URLLC users and EMBB users at the same time, because EMBB users would like to allocate huge resources in this grid, while a URLLC user will come, and if it doesn't see any resources, basically it's going to face a lot of delay. So we said, can we solve this problem by using reinforcement learning? And we started by trying first a Q-learning technique. Because we were using Q-learning, we didn't want to have too many states and actions, because of the problems I explained before. So we defined a state which is controlled by SANR, that is the data that we receive from the environment, which is a direct feedback that comes to LTE and 5G as the CQI value. So if the SANR, CQI stands for Channel Quality Index. If the average SANR is above a certain threshold, we say we are in the desired state, otherwise we are in an undesired state. So we formulated a reward function which would drive our agent into a certain behavior. And that behavior is related with both latency and SANR, because SANR is important for EMBB users and latency is important for URLLC users. So what happens here is that if the average SANR is above a certain threshold, then we can give a reward to the agent for allocating those resources, but the award will be partial. It will be in relation to the amount of time that the URLLC packets spent in the queue. And 1 is here because for URLLC traffic, our target delay is 1 millisecond. But these values could change depending on the problem. So with these, we were able to show that our technique performs much better than, especially under high load, in comparison to a technique that was called priority proportional fair. That was, I think, proposed a couple of months before our work. And over here, we see the URLLC latency play out. So for high loads, we have we can have lower delay. For low and moderate loads, it's almost equivalent, but at the high loads, we have a better latency distribution, plus the throughput of the MBB users and packet drop rates are better than the priority-based proportional pair algorithm. So after showing some improvements with Q-learning technique and resource allocation, we started looking at a more 5G specific problem where we have directional beams, directional cells, and these cells are basically they can have the users, a user might be in the coverage of multiple beams or multiple cells, and in that case they would be faced with interbeam intercell interference. Now, if we are using OFDM or if we are using frequency separation, that might be an easy, well, relatively easy problem to solve. But we wanted to look at a challenging scenario where NOMA, non-orthogonal multiple access, is used. So as some of you might know, NOMA assigns the same PRV blocks to multiple users, but the separation is done by the difference in the power levels. So that actually creates quite a challenge for the receivers because they have to do successive interference cancellation to figure out their own transmission, to find out what was being transmitted from the base station. So if there is interference, that technique is really vulnerable to high interference. So we said, can we use Q-learning for joint user cell association, basically decide which of these users will be connected to which beam or associated to which beam. And then can we work on beam power allocation, or can we jointly decide the beam power allocation such that the interbeam intercell interference would be minimized? So I'm just going to put them all over here. We have the agents as GNB, the base station, who's taking the decision. The decision, as I said, is, as before, user cell or user beam association and deciding on the power for the beam. States and rewards are again simple because we are using a Q-learning technique, and the state actually is the same with the previous work that I showed, but the reward is here much simpler because we are only looking at EMBB users. So if the SNR is higher than a threshold, we reward the agent with 1. Otherwise, it's a wrong decision. We penalize it with -1. Now, first, let's look at the plot on the right-hand side. We have shown that the sum rate of EMBB users can be improved significantly in comparison to a uniform power allocation algorithm. However, we have also observed that the convergence time can be quite long. So here we see 2500 TTI, which means that if we are to use such a machine learning technique, we have to do some offline training. And there has to be stationarity in the data. So the concept shift or domain shift, well, concept shift actually, should not happen such that, new learning curves should not be triggered. Under this, understanding, we said, okay, we can have a technique that can give us really good performance, but this convergence will always be a problem. We started looking at different techniques, and later in this talk, I will talk about some of these techniques. But before I get into those, I'm going to just explain one more thing, and then we'll talk about that really interesting work that we did. I mean, all of them are interesting, but that one is the most recent one, and it is one of the first works in the area. So this one, another interesting work of ours, is again working on a millimeter wave 5G system where we have the beams, but this time we are working on mobile users, and we are using 2 different machine learning algorithms. You might be familiar if you're working on data and unsupervised learning, you're probably familiar with the DB-scan algorithm. It's a very fundamental algorithm. So it is used to cluster users, and we use geographic information of the cars and the UEs to cluster them and follow the clusters with the users. And once we cluster the users, we set a beam for these users, and under each beam, we decide on the resource allocation. this time we use deep reinforcement learning. So we said, okay, Q-learning techniques are good, but it creates a limitation about the states and action space. Now it was the time to switch to deep reinforcement learning, and actually we showed really good performance with that, and we did that in our 2020 GlobeCom paper. For the deep Q learning, we use an LSTM-based deep Q learning. I explained how LSTM is used and why it is actually so important. And with this technique, we showed that, so we have actually three different things, sorry, to look at. Number one is the latency of URLC users that we can look into these two plots. For low load regime, we show a good performance in comparison to a k-means based priority proportional pair algorithm, KPPF for short, and our algorithm DQDL. So DQDL shows a good performance for a low load regime, but also at the high load regime, it is superior to the other algorithm. Plus, if you look at the sum rate of EMBB users and sum rate of URLC users, we see that our algorithm shows better performance than what was proposed by the KPPF algorithm. So with these, we were able to show that either using Q-learning or reinforcement learning, we are able to improve the performance. But that problem of convergence always, is something that has been lingering in our mind, and we said maybe we can find a solution to this. So we went back to the machine learning literature and look how, people in different domains solved it. And we came across a transfer reinforcement learning technique, which was used in robotics. So, and it's actually very intuitive. I mean, if you think about a human learning something, we don't always learn things from scratch. We use prior knowledge. So why can't we make machines use the knowledge that they have obtained in a prior task in a future task? So that's what we did in our paper. That was one of the first papers on transfer reinforcement learning, that we trained some expert G-node Bs on different tasks, which is an omnidirectional setting, and only user cell association decision is taken. And the learner G-node Bs learned from the experience those experts and did user cell association under a directional cell setting. So it's not exactly the same task. And also the selection of number of beams. So two decisions are taken at the learner level. Because of the omnidirectional setting and the directional setting, we have different channel models for the experts and the learners. But when we look at the results, and both of them are using machine learning, expert G-node B is using Q-learning, and the learner G-node B is using transfer reinforcement learning. So the expert G-node B has decent learning curve. But the most important part is the learner G-node B, because this is the G-node Bs that we want to actively have in the field. So they start learning earlier than the regular Q-learning technique. If we had been using Q-learning technique, it would be the blue curve. And plus, we are getting a better reward value. So with this work, we also showed network KPIs were good, but I'm not going to show all of these. So with this work, we showed that the convergence can be significantly improved. Now that my clock has told me that we are almost running out of time, let me go a little bit quicker here. So this is the performance results that I'm not really going to talk about, but we have some interesting work on ORAN, which is actually a new radio access network. And in this area, we decided on the dynamic function splitting in an ORAN, in a virtualized disaggregated network, where the DUs and CUs are powered by renewable energy. So depending on on the availability of renewable power, we said, for example, we're going to use option 7.2 or option 6.1 for different settings. And we used real data to drive our to drive our results. So we look at solar radiation and traffic patterns in different cities around the world for different cities. And we showed that dynamic function splitting that we implemented by using reinforcement learning can help us save the operational expense, to reduce the operational expenses for a network. Now, with this, I'm going to wrap up my talk. I like calling this time as the spring for AI. If you are familiar with some history of AI, there is this famous winter for AI, where there were funding cuts, and because of the NLP research was not progressing in the direction wanted, and a lot of people were driven out of the field. Only very enthusiastic people stayed, and luckily they stayed actually in this field. And then it wasn't really a bright time for machine learning researchers. But now in the wireless, I see that there is a lot of interest for applying AI and machine learnings. I like to call it the AI spring. It's not summer yet. I don't think we have the prime time techniques ready, especially because of the problems, the convergence problem that I mentioned. But still, there's a lot of interest, and I'm sure we can do a lot of progress. And the things that are contributing, the things that are contributing to this AI spring is that we have shifted to more software-centric designs, more distributed computation at the edge, and more disaggregation in the RAN field. We have challenges for sure. Convergence, I mentioned as one of the fundamental things. There's also the problem of scalability. So we have to, we can have schemes that work on maybe 1 to 5, 10 base stations, but would they work on hundreds of them? We need to make sure about that. And then another problem is lack of standardized training sets. And it's very hard to find data sets in this field. That's one problem. And most of the times we deal with distributed agents, and some of the times we have to learn from the rare events. So these are the things that are, the roadblocks that we are trying to solve in this domain. So with this, I would like to conclude my talk and give some time for questions as well. And of course, as usual, I would like to thank my students because they are the ones who are driving this great research. So thank you very much, and I would be very happy to answer questions.
Thank you, Professor Melike, and thanks for explaining the various topics very lucidly, starting from Markov decision process and how it takes us to the machine learning and the AI, and especially for the communication system and 5G system optimization. There are a couple of questions in the chat box. I encourage others also to post your questions. Just to start with, I want to ask one generic question. So you have talked about like optimization for reducing interference in the MIMO network, 5G network, and so on. And you also talked about the difficulty when you have distributed agents, and which is going to be the typical case in a network, like let's say the neighboring cells are doing their own resource optimization, and let's say if somebody is using multi-user MIMO in a cell, and of course the choice or weight of one base station is going, GNB is going to affect the other GNB in terms of their resource optimizations, choice of MIMO weights, and so on. So is there any theoretical study or analytical work done on when you have two MDPs and where the state of one can influence the state of other? Is there any convergence study done, or any interesting work that has been going on in that area?
That's actually a very good question, and it leads to a couple of things, and it will help me to explain maybe some of the things that I did not really touch upon in this talk, because in this talk I focused mostly on resource allocation side of the wireless problems, but there is a huge amount of research on the file layer as well, especially for multi-user MIMO, which has been challenging, and now we are seeing machine learning can come up with really good and strong techniques. So in terms of that, there are lots of studies in this area. And when it comes to convergence or divergence, when we have multiple factors affecting a decision, that's actually a very relevant problem to the machine learning community. So under partial observability, and it's a part of our research as well, how do we take the best decision under partial observability? And unfortunately, most of the times our problems are like that. One case is for could be for MIMO on the file layer. Many problems are like that. But even for resource allocation, many things are like that. We don't get the direct feedbacks, we get indirect feedbacks. We have very recent work on that where we use a technique called team learning that's going to be soon published in a conference. Federated learning is one other technique that, again, researchers around the world are quite fond of, and we are also using in our techniques, but I did not present it today. So these techniques allow us to work in distributed environments in a better way.
And I have one follow-up question on that is for this MDP or the reinforcement learning, the feedback what you get is always have some latency. There is a delayed information which is coming into the optimizer. So is there a study on the sensitivity of the solution or the optimality of the solution depending on how the latency of the information is coming in?
In general, yes, the latency in feedback is something important in machine learning. But when we look at the techniques that we design and the feedback that we use from the environment, this is actually the same feedback that the base stations already use in their traditional algorithm. So without a machine learning technique, there is already a traditional algorithm at the base station that the scheduler takes a decision, and that decision is based on the CQI that is being received from the environment. So we receive the same CQI, and we use a different algorithm to take a different decision, basically. So in terms of that, in our techniques, we don't see much impact of it. But of course, there can be another decision domain where the feedback is different, or maybe the feedback is not really defined in a way in a standard, because we are tied with how the feedback is defined in 3GPP. We are not creating any new feedback that is not available to the G node B. We are using what's already available in the standard. But if we were to go experimental or futuristic and try some other feedback, and that feedback has some latency, for sure that would be a problem.
Thank you. Yeah, let me read out the questions for you. The question by Rohit says, what kind of tools can be used to simulate the network environment in a practical research? He's questioning that whether the network need to be passed while learning occurring in order to learn the changes and then apply that thing to the network, what are the learning. So that, I think that is the question. Yeah.
So let me first answer the first question, what kind of simulation environments? In our work, we generally use either MATLAB or NS3. So some students prefer to do their implementations over MATLAB by using LT and 5G packages, and on top of that, we have our Mac implementation. We use that. Or some students are, quite familiar with NS3, and then they use NS3, which gives actually the advantage of using AI gym environment too, where we have the machine learning libraries. So any of them can be used if somebody wants to do research in this area, or there could be other tools too. And what was the second question?
Yeah, I mean, he was kind of explaining why he's asking that question. So yeah.
Oh, okay.
Just justifying that. Yeah.
Right.
So next question from Yeah, Mr. Sumit asked, you mentioned about lack of standardized data sets. So he would like to know whether you can briefly talk on the available data sets for evaluating the problem that we have discussed today.
Yeah, data sets is a big problem. And frankly, this is really important because what led the NLP field or the computer vision field to flourish so much, for AI algorithms in this field, to develop so much, was actually the availability of data sets. And for the wireless communications, unfortunately, we don't have a lot of data sets, and it's mostly because of the privacy reasons. So operators, rightfully, wouldn't share private data of the users. So we really need some test environments that we can, maybe mimic some user behaviors and generate data. There are several efforts around this. I'm aware of one that is being done at Northeastern University. I know about the intention, but frankly, I don't know if they have the data sets available to the public at this point. But I mean, many of us in this research area, we acknowledge that there is a problem, but it is not a very easy problem to solve because getting the real world data from the operators is not something very easy.
Unless they come forward and share the data. Yeah, there's a related question by Ms. Himani. He says, how do you generate the data set, synthetically or experimentally? I mean, that's probably, I think you answered that. Yeah.
Yes, but in our case, actually, let me explain this, because data sets are important when you are using, let's say, supervised, non-supervised learning algorithms mostly. For the reinforcement learning case, what's more important is to have a realistic simulation environment, because we are not looking at an offline data set, and we're not trying to analyze an available data set. We are interacting with the environment. So as long as the environment is realistic, we're not collecting data in our research. We simulate the environment, we get the feedback, the CQI feedback from the environment, and the agent takes an action accordingly. That's why, I mean, if the question is which data we are using, it's not the data, it's the simulation environment that matters for us.
Thank you. Just one question by Jnanapriya. Thanks for the excellent talk, and follow-up to your green ORAN topic. Can you share your views on one, building energy efficient networks, two, energy saving optimization in RAN sharing, and leveraging AI techniques? Yeah, it just, yeah.
Well, actually, energy efficiency tends to be a very, very important topic, and I believe in 6G it's going to be a very central topic too, because a lot of the governments are pushing for sustainability, and we all know that network equipment comes with some amount of energy consumption. So whatever we can squeeze out of it, whatever we can save from it is important. We actually have today. Was there another question or?
Yeah, it's just a related question. Basically, she wants to know your opinion on the green ORAN, how it helps to build energy efficient networks and energy saving optimization in RAN sharing and leveraging on AI techniques. That was the second part of the question.
Yeah. I mean, in general, yes, it's a problem, and we have research into that. And there are a couple of ways of doing energy efficiency. The Green ORAN paper, for example, that we had, focuses on using renewable energy. So the assumption here is that we have CUs, centralized units, and DUs, distributed units, that have computational resources, basically data centers, that can process the RAN functions. And they have solar panels on top. assumably. And we say during there is high solar penetration, we shift the load to the, let's say, more, if there's a CU that's more capable of generating solar power, we shift the load to that CU. So that's where the green part comes in that green ORAN network. In terms of RAN sharing and those concepts, I think it will be very important, although I don't have any direct research in that area, so it will be a bit hard to comment, but at least I can say, you know, this is an important area. And yeah, as I was saying, energy efficiency can have two dimensions. One is considering the availability of renewable energy and how to maximize the use of it. And the other one could be basically squeezing the amount of energy that we use while still the base stations or the equipment are powered from the utility grid.
Okay, thank you. One question from Subhas. Is there any study done on the energy usage in AI-based algorithm versus traditional algorithm? He's comparing the computational power, computational energy.
Yes, that's also very important. I mean, we might come up with a super good technique that optimizes the network performance, but then that technique, let's say it's machine learning based, that particular algorithm might be consuming a lot of power to do that task, so which would not be good. Based on what we do, but I mean, we are doing all this in, I would say, in toy models. So just one or two base stations, you know, very few interactions and these kind of things. We don't see a huge energy efficiency problem there when we use a machine learning algorithm or a traditional algorithm. But if we increase the scale of it, of course, that can be a problem. And I think that's an important problem that needs to be studied.
In the interest of time, I'll just take one more question. The other questions we can probably address it later, either over email or something. But question from Shiba, she says in interesting session, it was mentioned that the different channel models were used for the omnidirectional and directional, I assume, beams. Could you specify which models were used for either cases? I think she talks about your simulation, I guess. And the second question from her also says, will the modelless channel estimation perform identical or better than channel estimation with the existing models assumed in the framework?
So when we use, when I say we use omnidirectional model, I actually mean that's the numerology 0 in LTE, so 15 kilohertz subcarrier spacing between the OFDM subcarriers. And in that sense, we use the general capacity formula with the channel gains. When I said, or in a couple of the works that we used the directional cells, this is where we used different numerologies in 5G. And in that sense, when we use different numerologies and when we use different spectrum, we have a different channel gain. And the channel gain is impacts the directionality of the cell and also the propagation property. So as we go to the higher spectrum, as we start using spectrum from the millimeter wave, we know that we have high path loss. So we integrate this path loss into our simulations. We have the channel models driven from millimeter wave that are adopted in NS3, and those are the ones that we are using.
Okay. Thank you, Professor. Thank you for answering all the questions. And I know it's very late there, but thanks for giving this wonderful lecture. And I'm sure there's a lot of questions people have in their mind. And please post the questions to us. We'll try to get the answers from Professor. And with that, I would like to request Dr. Dilip to give the vote of thanks.
Thank you, Gana. Professor Mel, it was fabulous listening to you, and it was an inspiring talk. I'm sure a lot of engineers, students, researchers will take away a lot of information from this, and it'll help them do their research better. And in the work that you're doing is cutting edge, with ORAN and distributed computation and hybrid and distributed SON algorithms being developed with the RAPs and the non-RT-RIC interacting with the network, and we could have reinforcement learning in that framework. Your formulation would fit very well, as a general framework to develop different RAPs and XAPs and stuff like that to optimize future RANs. So it was beautiful to listen to you, and thank you very much, especially at this late time. You made time for us, so we were very grateful. Thank you.
My pleasure. My pleasure. Thank you very much. It was really a great pleasure to be with you today. And thank you very much for this very good questions. And I would encourage the audience, if I'm sure there are many questions that I could not answer. Actually, I had a quick look at the chat. So please feel free to email me, and I would like to answer each and every one of them. Thank you very much again.
Thank you. Gana, you're muted. Gana, you're muted.
Sorry. Thank you, Professor. And I would like to know the participant I would like to inform all the participants that the video recording of the session will be available in our YouTube channel. I have posted the link for the ComSoc Bangalore YouTube channel. Please subscribe to that so they'll get notification for when it is uploaded. Thank you. Thanks everyone for joining us. Thank you, Professor.
Very much. Have a good day. Bye-bye.
Bye-bye.